Hello everyone, we are from team MY053 of IMDC 2023 and our title is DNN Accelerator Implementation using 32nm CMOS and 7nm FinFET technology using ASIC design flow. My name is Jinjan Kit and this is my member Sheikh Muhammad Daniel, Sheikh Muhammad Najri. My advisor is Professor Madya Dr. Noor Ain binti Kamsani and we are from Faculty of Engineering UPM.
For the introduction, there is a rapid growth of deep learning. AI is widely used in different sectors, such as in virtual assistant, which is Siri, Bixby, and Cortana, in the automobile industry, and also in advertisement company. AI is able to learn what we like, what we need, and correctly predict the outcome. Shopee, Lazada, and Facebook always show our interested item based on the AI. But AI uses a heavy computational power. So we implemented our design on ASIC because a general CPU will have high latency and lower computing power. GPU will have high parallelism, run computation very fast, but it's very power hungry. FPGA will have high performance and reconfigurability, and ASIC will has lower power, optimized speed, and optimized power consumption. So the advantages of CPU is because it is conveniently available. CPU has high parallelism and very fast. FPGA will have flexibility and high speed. ASIC will have lower power consumption, lower area, and also fast speed. The disadvantages of CPU is because it has high latency, it has low computational power. GPU disadvantages is because it has high power consumption. FPGA is because it is not as optimized, and ASIC is expensive to fabricate. It has low flexibility and it is time consuming to design. So for CMOS versus FinFET, because our design is on 32nm CMOS and 7nm FinFET, the FinFET is 3D structured and CMOS is planar structured. So FinFET is significantly reduced current leakage, which results in more power efficiency. And it has better performance in terms of speed and power consumption. It also has high transistor density than the 32nm, and it will be more expensive to be manufactured since it is more complex. So for the problem statement, an AI chip requires a fast and low power consumption, and also we want cheap AI chips. So to increase that, we need to increase the transistor count, which will increase the size of the IC. So when the size of the IC is bigger, it will require larger area and it will result in more expensive. So we need to reduce the transistor size and length. But when we reduce the transistor size and length, it will have small channel effect, which will result in high leakage current. So we use 7nm FinFET to have small size and to squeeze more transistor in a smaller area. The FinFET can reduce the leakage current. For our aim and objectives, we aim to implement IC design of a DNN accelerator using 7nm FinFET technology. The objectives is to synthesize the DNN circuit into RTL and map it into FPGA for validation. To place and route standard cells and memory IP from 7nm FinFET PDK into the design, and to evaluate the design performance and make comparison with 32nm MOSFET technology. So for the ASIC design flow, we use the RTL codes with some constraints to synthesize it on Synopsys Design Compiler and Cadence Genus to get a gate level netlist, and we use that to place and route on Synopsys IC Compiler 2 and Cadence Innovus to get SPF file. So from the SPF file, we do static timing analysis. And also from the place and route, we will have DRC and LVS verification to get the GDS2. For the memory conversion, we get the codes for the DNN accelerator, which we refer to a GitHub. So the Verilog codes we will refer the Verilog codes from the GitHub, and we will convert it to Xilinx IP on the SPRAM, SDPRAM, and also TDPRAM to SRAM cells available in 32 nanometer and 7 nanometer. So the system Verilog codes of the memory and memory controller are then verified and synthesized using design compiler. And then after it's verified, we will include it in the whole DNN accelerator design to be synthesized together.
So this is what we did during prototyping, where we study the DNN structure and map the code obtained from GitHub to synthesizable Verilog. And then we determine the I/O ports of each module and produce the block diagram. From the left side, we can see that there is the DNN top block diagram, which has 4 inputs, which is the X0, which is the activation data with 512 bits, the ETA pause, which is the specific input position, the clock, and the reset. And then output, we have clock, the cycle index, the NSL, which is the ideal output, and XL or N, which is the actual output. And then on the right side, we have the DNN. The DNN is a 3-layer DNN, which consists of input layer block, hidden layer block, and output layer block. There are 1024 neurons for the first layer, and 64 neurons for the second layer, and 16 neurons for the third layer. The fan-in of the first and second layer is 8, while the fan-out of the first and second layer is 8, while the fan-in of the second and output layer is 128 and 32 respectively. The degree of parallelism is 512 and 32 respectively. And this is our design constraint for synthesis. We set the clock period at 2 MHz, which has the period of 500 nanoseconds. And for clock transition, input transition, and output delay, we set it at 0.001 nanosecond, and the input delay of 0.002 nanosecond, and a load capacitance of 0.05 nanofarad, and the area must be minimum. So we have successfully generated the synthesized the 32 nanometer CMOS and 7 nanometer FinFET. These are the schematic that generated. So what we did was actually we trying to map the SRAM because they are unsynthesizable to become synthesizable, and then we synthesize it. And these are the reports generated from the 32 nanometer CMOS. It shows that the total area is nearly 38 millions with slack of 584, which is no violation, and the power consumption of 13 watt. And then for the 7 nanometer FinFET from Cadence, we got a slack of 110116 picosecond, which is about 110 nanosecond, and the total area of 33,000, and the power consumption of 0.73 milliwatt. And when we see the comparison, we can see that at 2 MHz, there are about 11.5 times improvement in area, and a big 17K improvement in power consumption with no timing violation. So in conclusion, to perform in real time, DNN requires very fast and low power consumption chip. Thus, in 32 nanometer CMOS and 7 nanometer CMOS FinFET structure, we did a synthesis to test the performance of each design. So the result is that 7 nanometer FinFET shows that there are a significant improvement over the area, power consumption, and timing over the 32 nanometer CMOS. So so we can conclude that we have successfully done our synthesis part and to generate the gate level netlist, which can be used for the place and route in the future. That's all from us. Thank you.